Alright, so we have already introduced how to convert these documents into sets and how to generate the signatures for the documents based on the sets, right? According to the previous pipeline we showed before, the last step we may need to do actually is to calculate the scores among any pair of the documents. However, actually in the real world, when we are doing the last step, we may encounter some challenges. The main reason is because checking all the pairs for calculating the scores is very hard. So even though the signature of all the documents all may fit in the memory, however, comparing the signature of all pairs of the columns can be very time consuming, right? Because if we have like n documents, if we calculate the pair-wise scores between them, the time cost will be very high. So it is impractical to do this kind of pair-wise calculation of the similarity scores in the real world, and then we may need to propose a method to address this problem. So the technique we propose actually is called Locality Sensitive Hashing, and the high-level idea is actually to define a function fxy that tells whether or not x and y is a candidate pair. If these two are candidate pairs, then we can calculate the score between them. Otherwise, we can just ignore them, right? So the main target here is to define this hash function fxy to tell if we should compare x and y or not. So the way we define fxy's function actually is based on the hashing signature matrix we generated before. This signature matrix, this M matrix. So we define fxy's function based on the signature matrix we defined before for the documents, and we propose to hash these columns of the signature matrix to many buckets, and we can make elements of the same buckets candidate. And for the documents which are assigned into the same buckets, then we may potentially calculate the scores between them, because we may consider them to be more similar to each other based on the hashing results, right? If two documents are hashed into the same buckets according to this hash function based on their signature results, if so, then we may consider them to be as a candidate pair, and we can further calculate the score between them. Then the target will be how to hash this column to many buckets. So we do this way actually into several steps. So the first step actually we want to do actually is to partition this hashing signature matrix into several bands. What does it mean? What does this mean? So because we mentioned before, we have a signature matrix, this M matrix, right? Because as we have more signatures and more documents, this matrix can be very big, and therefore we propose to partition this matrix into several bands. What is a band? One band will cover several rows of this M matrix. For example, in this page we show you with example. This M matrix is the one we showed before here, right? And here we partition the M matrix into several bands. One band is one part, you see here, right? This one band, the second one, the third one, last one, as shown here, right? And each band in the matrix actually will cover all rows in the M matrix. So in other words, the size or the number of rows of this matrix M will be equal to B times R. So we name this submatrix as one band. And when we are retrieving the signature of one document, we may have to retrieve all the columns in all these bands for this document, right? Because the signature vector of this document may span across several bands actually at the same time. So according to the example, we will partition this M matrix into B bands for our rows. Each band has R rows. And for each band, we hash its portion of the column to a hash table with K buckets. But right now we didn't mention buckets yet. We just partition this one into bands, and we may retrieve the signature vector of the document in each band. Like for example, we can retrieve this part of this document, and we can further hash this part of the vector into a bucket, right? And so here we have a parameter is denoting K, denoting the number of buckets available for us to do the hashing. And we may make this K as large as possible, and this way we can distinguish each other from other documents, right? If this K is very small, for example, if we have one single bucket, then every document will be hashed to this bucket. Then this hash function will be useless because we may still have to compare any pair of the documents, right? This K will be then this bucket will become useless. Normally, we want to make this K as large as possible. In this way, we can make sure for two documents, if they are hashed to the same bucket, they are more likely to be similar to each other. And then we can candidate the column pairs, rows which are hashed to the same buckets for more than one band. Because for any two pair of documents, right? We may have B bands. In other words, we may have to hash its signature to the buckets B times. We may retrieve each of the signature portion in each of the band due to the hashing into buckets, right? In other words, we hash this signature of this document B times. And for any for any pair of documents, if we hash their signature to the buckets, to the same buckets for more than one band, if so, then we can make them as a candidate pair. So you can see in this algorithm we have several parameters. We have B, R, we have K, right? Normally we may have to tune the parameters to make sure this algorithm will work well in the best settings. And according to the previous descriptions, we can further show you how to do the hashings. According to the previous pages, we mentioned we can partition the matrix into B bands. And for all the documents inside each of the band, we can retrieve its signatures. It is just one part of its overall signature, right? Because we can retrieve its signature within this band. And we can define a function to hash the signature vectors into a bucket. Right? Like here we have K buckets. If we have ever hashed through any pair of the documents to within the band to the same buckets, if so, for example, this column 2 and column 6, they have been hashed into the same bucket, right? If so, then they can be potential candidate pair and should be considered as similar pairs actually. So this is how to partition them into bands and further partition them or hash them into the buckets for considering them as candidate pairs. And in this way, we can shrink the search space greatly, and we don't need to calculate the pair-wise scores anymore. We just need to consider the pairs which have been partitioned or hashed into the same buckets in some bands.